what we had on the previous slide, that required relevance judgments. So I had to know which pairs were positive and negative. And in a competition, you know that, because in a competition, somebody's going to go and annotate which documents were relevant and non-relevant for each query. But if you're Google and if you work on the web, you have something much better. Well, it's simultaneously much worse and much better. It's much worse in the sense that it's not relevant. It's much better in the sense that you have tons and tons of these examples. Right? You have clicks, and clicks, as we said, indicate preferences. So you had a ranked list, user clicked on D3, you have a set of preferences that come up from that. The user preferred document 3 to document 2, preferred document 3 to document 1. So how can we use those things instead of relevance judgments? We talked about how we can use them for evaluation. Remember the Kendall Tau or the BPREF. But how can we use them directly for learning? Because they're not relevance. And the answer is really simple. If for each one of those pairs that you generated, you know what the user wanted. You know that the user clicked on D3. This means that the user wanted D3 to be above D1. And the user also wanted D3 to be above D2. Right? So take those and create constraints, SVM constraints, out of these preferences. So for each pair of documents where DJ was preferred to DK, I'm going to have the following constraint. The dot product between the weights and the DJ, so think about what that means. This means a score, a weighted combination of features for document DJ. That's the meaning of this dot product. This is a weighted combination of features for document DK. My score is just that weighted combination. And what I want is I want the score for DJ to be higher than the score for DK, so that DJ ends up getting ranked higher, right? Because at the end, you're going to rank by the score. You're going to sort by the scores. So I want that to be bigger than that. And it's a large margin method, so I'm going to introduce a +1. I want to separate the positives and negatives. And I'm going to introduce the slack variables as well for the cases where it's misclassified. So I'm going to have one of those equations for each preference pair that I get. Right? And the preference pairs you get exactly from clicks. Right? And then, of course, you can reformulate that as, you'll notice that this is the same weight vector. These are just the importance of the different features that you have. And you're multiplying them by the jth document and by the kth document. So I could just take the difference between the documents, multiply it by W, and have that. And that looks exactly like the SVM formulation that we had on the 2 slides back. Only now we have a difference between the 2 pairs, not just a single pair. You can have a single pair if you know if it's relevant or non-relevant. In this case, you don't know which one's relevant and non-relevant. You just know that you want the score for J to be higher than the score for K. So you take the difference between J and K and treat that as a vector, as an example vector, right? Again, you know what the solution is going to be. It's going to have that centroid form again. Right? And good things to think about is think about the objective function that SVM is optimizing. Right? It's all fine and dandy, and SVM is an optimal algorithm, and it optimizes something. What does it optimize? What does SVM try to minimize? Oh yeah, okay, dumb, but really, what does it want to do? It's a classification algorithm. It tries to minimize the misclassifications, right? Or, put it oppositely, it tries to maximize classification accuracy. Right? Is accuracy a particularly good measure for retrieval? We talked about that. Not really. So it's a beautiful picture. There is one hole in it, which is that your objective function isn't particularly good, but the bad news is it's really hard to change that, because if you try to change it to one of the metrics that you would want to maximize, like mean average precision, you quickly realize that that's not differentiable, it's not continuous, and you cannot do anything with it, and you cannot come up with any kind of an optimization algorithm for it. Right? So you take accuracy and try to play tricks to make sure that accuracy somehow reflects what you're really trying to do. All right? And this is basically as close as we're going to get to knowing what Google does. Right? So when Google says PageRank, nowadays, they don't mean the PageRank algorithm. They don't mean the algorithm that talks about the popularity, or sort of the proportion of time that you're going to spend on a certain node in a graph. PageRank is really that. You have a huge set of features, X, which they're not revealing, and you have a powerful mechanism for learning an optimal combination of those features based on click rates. So you use clicks, translate them to preferences, and use that to learn an optimal combination of features. Right.